Hello, hello, hello. Welcome back to class. How's everyone doing? I have been attending a virtual conference all week, and the conference itself is awesome, but man, it is really hard to pay attention to talks in your own home. I sympathize with the students now having to watch so many lectures. I could barely stay awake watching so many talks during these conferences. It was brutal. So, here we are in the course. We have just released assignment 3, but I'm going to say this was a feature instead of a bug, but I forgot to put the assignment on my website. And so I just checked, it's not there yet, and nobody has said anything. So that means nobody has gone to start it yet. So that's good. So I'll put that up there this evening. So the assignment will be there this evening. I can tell that nobody has started it because nobody has sent me an email complaining that the assignment isn't there yet. So you still have lots of time to do it, so I wouldn't worry about that too much. So we talked about all the stuff to do assignment 3, and we're about to talk about all the stuff to do assignment 4. And so today we're going to be talking about raycasting and line intersection. Someone in the chat says, I was being nice and thought it wasn't up yet because you were grading the AI midterms. That is actually probably why it was. I've just been super busy and I just forgot to drag it over to the folder. It's already done. I just need to do that later. So that'll be up there tonight. I'm sure no one's going to work on it before 5 or 6 p.m. anyway. So today we're going to be talking about raycasting and line intersections, what those can be used for, the mathematics behind them, and of course we're going to be doing the 2D versions, not the 3D versions. But once you know the 2D versions, it's not that hard to make the leap from 2D to 3D. But our game engine is in 2D, so why not do it in 2D? Also, before I get started, just wanted to share something I learned about this week. So if you're using Windows 10 and you go to the Windows Store, there's this app called Windows Terminal. And it is really, really good. And if you have WSL, so Windows Subsystem for Linux, installed, you can just like open new Ubuntu shells in Windows Terminal. So here I have a PowerShell, here I have an Ubuntu shell, and here I have a command prompt all in the same window. And like you can see here that this is like a fully functioning Ubuntu, so I don't need to be SSHing into the university servers to do my coding anymore. I can just do it all here with WSL and the Windows terminal. So yeah, this is pretty cool. You just install Windows Terminal, you go online, you Google how to install WSL2, and then you have this for free, which is pretty nice. The only caveat to that is that if you have WSL up and running, that requires the Windows hypervisor, which means that virtual machines will no longer work. And I don't know the technicalities behind why one will work and not the other at the same time, but that's all. Okay, so let's have a look at today's lecture. Let's get into the PowerPoint. Cool. Let me grab a drink real quick before we start. So today we're going to be looking at two things which are very, very related. 2D raycasting, or you may have heard of it as ray tracing. Ray tracing is just iterated raycasting. And also, why isn't my laser pointer working? There we go. And also 2D line segment intersection. So 2D line segment intersection is required for 2D raycasting. So we'll talk about what raycasting is to give sort of the context for it, and then we'll look at the mathematics behind it. And you will be doing this on assignment 4 and on the project, so that's why we're learning about it. So what is raycasting exactly? Raycasting is the name for a technique which has many applications in games. So if you've ever heard of ray tracing before, ray tracing is just iterated raycasting. And we'll see that raycasting involves finding a light, a Oh, well, we'll see what it is. Intuitively, in 3 dimensions, what it means is, if we're talking about lighting, for example, or vision, then raycasting is I'm going to cast rays outward from my eyes to the world, and if I do, what do they hit? Okay, so I'm gonna be simulating vision by casting a bunch of lines out from my eyes and seeing what they hit, and then those are the things that I should be able to see in my scene. And it's pretty heavy on the vector math, but it has many useful applications. And a lot of the AI systems in games involve raycasting for things like vision. Can the enemy see me or not? Its behavior is dependent on that. You can, for example, envision like if you have a turret, like in the Portal games, well, they don't even activate until they can see you. If you have hit scan weapons in video games, like for example, we've been doing examples in our games of a bullet which travels out slowly, right, a projectile. But if you have a hit scan weapon, that doesn't have any sort of travel. It's not actually doing those sorts of step-by-step collision detection. And so hit scan weapons use ray tracing in order to determine what they hit or not. Someone in the chat asks, dang, are we implementing RTX? Yes, we're going to implement RTX from the ground up. Not really, though. Okay, so raycasting and ray tracing. In 3 dimensions, this is actually RTX, right? So this is ray tracing. You have some camera. This is the real-life version of this, right? So if you're a photographer or if you've ever taken a picture, this is essentially what's happening. You've got the real world out there, and you've got some objects in the real world. Now, of course, you're not going to see anything without light, right? So your eyes being able to see things, it's really crazy to sit down and actually think about this in terms of like what vision actually is. But it just so happens that we have these organs that when light bounces off something, and then that bounce happens to hit our eyeball, we sense it as a different colored light, and then our brain processes that into what we perceive as the universe. So with a camera, what happens is that the camera is going to produce some image here, like this 2D plane. Like, we can't take a 3D image yet. Well, we kind of can, but basically a camera takes a 2D plane of an image, and that image plane, what ends up in the image is the intersections of these lines between the camera lens and the real world when light bounces off of it, okay? And so there's all these bounces involved. You know, you may not think of a surface as being reflective, but if you can see it, it's reflecting light. If you can't see it, it's not reflecting light. That's basically it, right? So pretty much everything in our normal day lives is a reflector. It's reflecting some amount of light to our eyes. So how do we actually do raycasting in video games? Oh, and just to let you know, these calculations may involve multiple bounces, right? So it may go from a light source, the light may bounce off and hit one object, and then go hit another object, and then hit another object, and finally end up at our eyeballs. But we're not going to be doing that in this course. It's a little bit out of scope. So, raycasting, how do we do it in our actual game engine? Well, we're going to be drawing a line between 2 points. And when we draw that line, we're going to detect if and where a collision occurs on that line. So ray tracing is sort of like, where did it bounce to, right? Because we have to calculate one line, and then where it intersects or where there's a collision, we then take that angle and we bounce it again. And so ray tracing is the iterated raycasting, which asks, where is this going to bounce to? And then you keep going for like some maximum amount of bounces until it either ends up at the camera or it doesn't. If no collision occurs on a line between 2 points, then they can see each other, right? So if we have a line and there's no collision with any other line or any other object, then we call that a line of vision or a line of sight, okay? So if you've ever heard of line of sight in video games, that's how this is being calculated, is with this raycasting. So 2D raycasting primarily solves problems that deal with light or visibility. And when we talk about visibility, we also talk about like hit scan weapons and stuff like that. So for example, here we have an example of lighting, right? So here we have an image in which there's a light source. This light source, actually, can I? Yeah. Okay, let me restart. This light source, we're trying to figure out where in the map should be lit up or not lit up. Where should be shadows and where should be light? Where can we see and where can we not see? And so what we're going to figure out, we're going to actually solve this problem in this class today by computing these line segments. What is behind the line segment intersections with other line segments is going to be shadow, and where there's no intersections, there's going to be light. And then if you want to take this to the next step and you put in some things like shaders and stuff, then you can make this look really fancy. But essentially, you do this calculation for one light source, and you iterate that, and you do it for every light source, and you can have really cool images pop up like this. So there's an article on visibility here, and I'm going to bring that up because it's a really nice demo, but I'll do that at the end of the lecture. And so here, for example, this is going to actually show you how you get from a situation where you have just one light source and casting out rays to actually producing what's visible in the map. And we're also going to be going through another tutorial on a really cool website for something that you're going to have to implement for the project. So make sure you pay attention to that part of the lecture. So here's an example of a game called Third Eye Crime. This is from Moonshot Games. And in this game, you have to get through a level undetected by these sort of detectives in the level. So here you're playing this criminal, so you have to go from one point into the map to steal a briefcase or something like that. And so here you saw at the very beginning, let me restart this, the player picks up a briefcase, and then the NPCs have these vision cones, and you're trying to avoid the vision cones and get to the end of the map. And so by the end of this lecture, you'll actually know how to implement something like this. So you can see here that this is the vision radius, or the vision cone of these enemies, and you're trying to stay out of that. Okay. Similarly, we can also do things like lighting calculations, and all of this is the same calculation. So you'll know how to do this by the end of this course. And I want you to be doing something like this in the project, and it's going to be really cool, and it'll add a lot of really cool features to your game. So here we have a light source, we're dragging it around the level, and we're saying anything behind, right? So the real world example of this is a light source, it's hitting some object in the world, everything behind it is a shadow, everything that's not collided is a light. And so we'll figure out how to do that. But in order to run, we have to learn how to crawl, right? So let's look at that first. Yeah, so someone in the chat said Among Us. Yep, so you'll be able to make a game like Among Us if you want to, maybe minus the networking. So, raycasting basics. Raycasting essentially asks the question, is anything blocking the path between these 2D points? So here we have point 1 and we have point 2. And we have a line segment. And our games for our project are pretty much going to be made up of these line segments, right? Most game geometry is made up of triangles or planes or line segments. And so asking the question, does one line segment intersect with another line segment, is a very important question. So how do we detect this mathematically? Well, the path between 2 points is blocked if the line segment between these 2 points intersects with another existing line segment in the level geometry. So what that means is if we draw a line segment from point 1 to point 2 and that intersects with another line segment, then this would be considered blocked, okay? So for example, if we're here at point 1 and we're asking the question, can we see point 2, then the answer to that would be no. And so we've detected that there's an intersection. So that's the first form of raycasting. It's just basic line segment intersection, which is returning a Boolean, is there an intersection? And the answer to that is yes or no. The next step is not only is there an intersection, but maybe where is the intersection? So depending on the application, we may also want to know where the first such intersection occurred and where it occurred, right? So for example, if I'm shining light somewhere, so if I'm shining light out from P1 to P2, then it doesn't make sense for light to hit all these things, right? It only makes sense for it to travel from P1 and hit the first wall and then stop there. And so what I want to know is not only is there an intersection, but where was the intersection? And not only that, but where was the first intersection? Okay, so this is what we want to calculate, is not only the Boolean, but this location right here. So far in the course, we've been using the vec2 class to represent points in 2D space as a 2D vector with x and y. So we're all completely familiar with 2D vectors, right? So a line segment can be defined by the start and end point of a line segment using a vec2. So here we're looking at two vec2s. So instead of like putting on the slides all the x and y coordinates and stuff, we're just going to use these vec2 variables here. So here we have vec2a, here we have vector b. Okay, so we call this line segment AB. So again, if it starts at one point and ends at another point, it's called the line segment where it started and where it ended. Time for some more vector math. So here we have points A and points B, and they're stored as a vec2. And here we have line segment AB. So what we can do here, just to start off, we're going to talk about scaling vectors and how that's going to help us calculate line segment intersection. And again, just as a caveat, like everything in this course, this is not the only way to do this, but it's pretty efficient, and it's going to be very understandable and very implementable in your games. And in fact, I'm basically going to give you the function in the slides, and all you have to do is translate it to your code for assignment 4. So let's do some vector subtraction here and see where we get. Let's take a little journey into vector math. So let's do r. So we're going to find vector r, and that's going to be b minus a. And we talked about last time, if we take a destination and we subtract it from an origin, then what we get is the vector pointing from the origin to the destination. So here, b minus a equals r, and r is the vector pointing from a to b. And now what we're going to do is we're going to scale r by a scalar, okay? So we talked about scaling a bit last time, and essentially what we do when we scale a vector by a scalar, which is just a floating point number in our system, is we take the scalar and we multiply both the x and the y components of our vector by the scalar. So for example here, this was r, right? So this is the entire vector r. It goes from a to b. And so if we multiply r by 1, then we get the exact same vector. And so this is 1 times r. If we instead have 0.5 times r, and again, my precision might be off a little bit, but this is essentially what we get, is we get a vector pointing in the same direction, but it's half the length. And so 0.5 times r points from A to the midpoint of line segment AB. If we then make something bigger than 1, what we get is we get 1.3 times r, for example. We get a vector which goes beyond B, okay? But it's in the same direction. Now similarly, I don't have a slide for this, but if I had a negative scalar, then things would be pointing in the opposite direction, okay? So it would go from A, and if I said, like, for example, negative 0.5, then I would have this vector right here, because it would be in the opposite direction because it's negative, and it would go about half the distance from A to B. Okay, so what we're going to do is we're going to call the scalar on vector r t, right? So for example here, this is t times r, where t is equal to 0.5. So again, we're just taking that variable, this variable 0.5, 1.3, negative 0.5, all that kind of stuff, and we're going to just call that variable t, all right? And so here t is 0.5, and here t is 1. So what we can say is that when t is equal to 1, b is equal to a plus t times r, right? Because b equals a plus r, so if t is equal to 1, then b is equal to a plus t times r, okay? Now we're going to do that thing again we're just going to do it with two different points. So I don't have to go through all that math again, but we have a and b, and we have t times r, which is the vector being scaled, the vector from a to b being scaled by a scalar t. All right. We also have points c and d, and here we have the vector s, and we have a scalar u, which is going to be scaling that. Okay. So we add another line, points c and d. S is equal to d minus c, and we're going to scale s by a scalar value u. So when r and s have the correct lengths, the segments intersect. This is going to be really interesting. So in order to find where they intersect, if we find the correct scale values for r and s, okay, that's where they meet. And so now we can sort of figure out where our line segments are intersecting. So let's look at an example here. I've constructed this example to be very, very easy. But if I set t equal to be 0.5, and I set u equal to 0.5, then if I say a plus 0.5 times r, and c plus 0.5 times s, I get the same point for the result of those calculations. And so if I get the same point, it means that those original line segments are intersecting at that point. Okay, so that's the logic we're going to be using to find our line segment intersection. So we have b equals a plus t times r, remember? And where t equals 1. And we have d equals c plus u times s. The lines intersect when b and d essentially are equal. So if we scale back u and we scale back t to the points where the b and the d are now the same point, then that's where our lines intersect. So if we want b to equal d, then we just put their equations on opposite sides, right? So here, b is equal to a plus t times r, so we put that on one side. D is equal to c plus u times s, and we put that on the other side. And so when b equals d, we have the intersection. Now, there's one other thing here. Can anyone tell me out in the chat what I haven't mentioned so far? There has to be a condition on t and on u to ensure that if these are equal, then the lines intersect. Can anyone think of what those conditions might be? Okay, so one person out there said that they have to be greater than 0, and then right away the next person said they can't be larger than 1. Perfect. So the lines intersect if both t and u are between 0 and 1 inclusive, right? So if they're both 0, then they're both the same point, right? So that's a trivial example. If they're both 1, then b and d started at the same point. So if the two values are greater than 1, then what that essentially means, oh, if I can get my pen out here, if the value is greater than 1, then the point is out here somewhere where the intersection is, right? And if the point is out here for the intersection, then the point did not actually intersect on the line segments. It intersected on the infinite ray that was cast beyond the line segments. Similarly, if either of them are less than 1, then the intersection happened out here somewhere, which again is not on the line segment. So we are only on the original line segments if both t and u are between 0 and 1. So that's just one extra condition that we have to put on this equation. All right, so let's look at how we derive this formula now. So we have a plus t times r equals c plus u times s. So we're solving for t and we're solving for u. But what's the problem now? What did you learn in your high school math course about equations and unknowns, and why are we looking at a problem here? How can we solve for... What's the problem with solving for t and u in this equation? Can anyone tell us that? Uh-oh, someone got it. So someone just said two unknowns, not like this, right? So essentially, we have n equations where n equals to 2, and we have n unknowns where n equals to 2, right? So if we have the same amount of unknowns as we have equations, then that's going to be really hard to solve. So how do we solve for two unknowns with these just two here, okay? But some people are saying make a system of equations and do all this crazy stuff. Nope. We're going to introduce some tricky math that lets us just solve the problem for free, okay? Well, not for free. We have to do a little bit of big braining. But we're going to talk about the 2D cross product. All right. So first, the 3D cross product is the following. So the 3D cross product is represented by A cross B. So this is not the multiply star. This is just an X, and it denotes the cross product. And what this does is in 3D math, if you have vector A and vector B, right, which define a plane, and you have A cross B, that produces a 3D vector which is orthogonal to both A and B. That's called the normal vector to A and B. And what this is used, it's used for a ton of different stuff, okay? But it doesn't really make sense when you apply it to two-dimensional vectors, because how do you get into that third dimension? What is an orthogonal vector to two? There's no other dimension, right? So we can't get out of the two dimensions. So the 2D cross product doesn't have a lot of intuitive sense in two dimensions, but it's still a valid equation that can give us some nice properties that we can use to help solve that original equation. So the 2D cross product, A cross B, is equal to the X component of A times the B component of Y minus the Y component of A times the X component of B. So that is the equation of the cross product, and we've just defined it as that, okay? This produces a scalar value. So that's going to be really nice. And here's some important properties. If you take A and you cross it with itself, you get 0. Okay? So A cross A is equal to 0. Now you can start to see how this is going to help us. Also, if we have A plus R, so we have two vectors that we're adding together, and we cross the result of that by S, then we can do the separation of these individually. So A plus R cross S is equal to A cross S plus R cross S. So we're going to use these two properties to help us solve our system of equations. So let's solve for t now using our previous equation, which we had. But what we're going to do is we're going to use the cross product. So in order to solve for t, we want to eliminate the variable s. No, we want to eliminate the, well, we'll see. Okay. So we're going to apply the cross product of s to both sides of this, okay? So remember, when we're solving equations, we can do the same operation to both sides, and we'll have done nothing to the system of equations except possibly eliminate some variables. So here we'll take the left-hand side, and we'll cross it by s, and we'll take the right-hand side, and we'll cross it by s. So what do we get here? We get a cross s, right? Because we take a plus t times r is equal to this. So we'd have a plus t times r cross s. That becomes a cross s plus t times r cross s. Because t is a scalar, so we bring it outside of this right here, okay? So t times r cross s is the same as t times r cross s because it's a scalar. We do the same thing on the other side. So now we have c cross s plus u times s cross s. Oh, but what did we say last time? Right? We said that anything cross itself is just 0. And so that's going to help us out a lot here. So now we know that a cross s plus t times r cross s is just equal to c cross s because we've been able to eliminate this term now because anything times 0 is 0. And let's rearrange this now. So, so we're going to leave t times r cross s on the left-hand side. So we want to bring this term over to the right-hand side. So what we do is we subtract this, okay? So we subtract c cross s minus a cross s, and we get this. But we can use the shortening of that because we have c cross s and a cross s. So we can bring this C and A into the brackets, and now we just have C minus A cross S. So the last thing we have to do in order to solve for t is, since t is multiplied over here by r cross s, we have to take this and divide it by r cross s. So we divide both sides by r cross s. So t is equal to c minus a cross s, all divided by r cross s. And so that is our equation solving for t. And now we do the exact same thing, but we solve for u, right? So we have, I'm not going to go through this as slowly, but we multiply the cross product of r for both sides. We did it for s last time. So now we've crossed both by r. Now we get an r cross r over here that we can substitute with a 0. So we get the same equation as last time, except we're eliminating t instead of eliminating u. And we work this out, and we get u is equal to a minus c cross r divided by s cross r. Okay, now let's use that to solve. So we have t equals our equation that we just found, and we have u equals the equation that we just found. And we know all of these values, and we know all of these values, so we can get our values for t and u. But here's another cool property of cross product, okay? We have r cross s is equal to negative s cross r. And so what we can do is we can take this, where we had u equals a minus c cross r divided by s cross r, and because we're going to do two flips, we have a negative on top and a negative on bottom, and we can cancel both of those. And so what we get is that u, we can rearrange this. So we flip this one, and we put a negative outside it, and we flip this one, and we put a negative outside it, and so the negatives cancel. And so u is now equal to c minus a cross r divided by r cross s. And so why did I do that? Why would I have taken it from this form to this form? It's the same number of equations, right? But here's something really cool. Look at what we have now. This is the optimized version. T and u, right? C minus a is now used twice. Look at that. And r cross s is now used twice. And so we can compute them just once and then store them in a variable and to save some calculations, okay? And whether or not this actually saves you like actual time in your game, you would have to benchmark, but it's less calculation, so I just wanted to show you this version. So here's the final version. We have t is equal to c minus a cross s divided by r cross s, and we have u is equal to the same thing, except s and r are different. We have an intersect, so we solve this, we get our values of t and u, and we have an intersection if t is between 0 and 1, and u is between 0 and 1. And then all we have to do to get our point of intersection is we have t and we have u, so we just plug those back into the, we plug them back into the original equation. So once we've solved for t, we can either, we've solved for t and u, so we can either plug t back into a plus t times r, or we can plug u back into c plus u times s. And then we get the point that our intersection must have happened on. So that's the math. Let's look at some code, okay? So in assignment 4, I'm going to give you this intersect struct. And the intersect is basically going to store two things. It's going to store a Boolean, and that Boolean is whether or not there was an actual intersection. And the position is going to be, if there was an intersection, where was the intersection, okay? And we're going to have a function, which is line intersect, and it's going to take in 4 vec2s. It's going to take in A, B, C, and D. And those are the endpoints of line segment AB and line segment CD. And it's going to return as the answer this intersect struct, okay? And remember, a struct is just like a class, it just holds some variables. So first, we're going to construct our R vector, which is B minus A. Then we construct our S vector, which is D minus C. Then we're going to compute R cross S, and this is just equal to R cross S. Now, what we're going to have in assignment 4 on our vec2 class is a cross operator, right? So I don't need to put all the individual x and y math in here because the cross operator is going to be defined on the vec2 class. So rxs, that's a variable that I'm going to be setting equal to r cross s because r cross s is used twice in our calculation, remember. Also, I'm going to have a vec2, which I'm going to pre-compute, CMA, and that's C minus A. So I'm going to store those two values because I'm going to use them twice. Then I'm going to compute T, and T is just CMA cross S divided by RXS because that's the equation. And it's the same thing for U, except it's R instead of S. Then I just come in here and I say, if T is between 0 and 1 inclusive, and U is between 0 and 1 inclusive, I return true because there was an intersection, and then all I do is use the A plus T times R equation to figure out the point where the intersection was. Otherwise, if T and U weren't between 0 and 1, then I'm going to return false, and it doesn't really matter what this vector is, so I'm just going to put it 0, 0. And so that's how we do line segment intersection. Okay. Now we know how to do line segment intersection, but how do we actually use that for visibility, right? So if line segment AB does not collide with any vision blocking entities, then B is visible to A. Really simple. Excuse me. So for example here, yes, line segment AB collides with another line segment, and so AB is not visible A is not visible to B. If we had multiple lines here, we could do the same thing, right? We're just going to check, is A visible to B? Well, if it collides with any of these line segments, then it's not. But what about non-line in-game objects, right? We're talking about entities and stuff. So we've got entities which we're currently viewing as rectangles. Well, this is really easy because they're made up of line segments, right? So we can just take our entities, figure out the line segments of the bounds of the entities, and then do those collisions. So for example, if I'm trying to figure out, okay, the line segment intersection between A and B, then I can come up with this. And so the entity that can be seen is the one that's up to the closest intersection. So here I can see this entity, but I cannot see this entity. And anything beyond this one is outside the vision in between A and B. Okay. How can we use this for game lighting effects, right? Because we're talking about single rays here, but the problem is light travels outward in all directions. So how do we calculate it now if light travels outward in all directions? What we want to do is calculate everywhere that light lands, not just... So can A see B is a very... Can point A see point B is a very important calculation and is used for a lot of stuff. But if we're trying to do something like this, right, where we're trying to calculate everywhere that light can see, how might we calculate that, right? That is a little bit more complicated, but we can do it with almost the math that we've learned so far. Okay, now, there are several possible ways that we can do this. And so what I'm about to show you is just one of the more intuitive ones that I've seen, and one of the things that you're going to implement on your project, which will be really, really cool. And trust me, when you start to see effects like this in your game, you'll be like, holy crap, like I have an actual game here, right? And that'll be really cool. So what we're going to do is I'm going to shut down the PowerPoint, and I'm going to go to this website here. It's called Sight and Light, and it's a really cool online tutorial that you can follow along with. And, discard. I just want to read one of the questions in the chat here. Okay, so I don't need to answer that in the class. So here we're going to go back to the website, and I'm going to bring up my spooky cam, and we're going to be looking at this website. So this is called Site and Light. It's a very great little tutorial on how to create the effect that I showed in the class. And if you notice here, the geometry, I just copied the geometry when I implemented this, okay? So how do you create this effect? So you've got little shadows around things. You've got, for example, if you can see the image of the person in the center, then it's, you know, red hair and uniform. If not, then it's a skeleton, right? So how do you do something like that? Well, I'm not going to read the entire tutorial to you because we've looked at a little bit of this already. I'm going to sort of put it in my own words. And so what we're going to do is we're going to have a point here that follows the mouse around in this website, okay? And so it talks about some of the math that we already talked about. This is a little bit different, but it is pretty much the same, okay? So the calculations, the math is a little bit different. Ours is, I think, a little bit more optimized, but it's pretty much the same math. So here what they've done is they've shown you, now that you've implemented that, let's draw a line segment that goes from the center of the screen to wherever my mouse pointer is. And let's figure out the closest intersection. And you can figure out the closest intersection really easily because you have a lesser or greater value of t, right? Okay, so right here, the circle is the intersection point either with an object in the game or with the bounds of the level. See how that works? And we know how to do that because all we're doing is taking every line segment in the level and doing the intersection check with it. And we keep the one that intersects the closest. Okay, now what we're going to do, because light goes everywhere, we're just going to cast rays in a circle. So we're going to take our circle, right? We're going to take our line, our point, which is currently at the mouse pointer, and let's say we're going to cast 30 or 50 or however many rays equally spaced radially from the center, and we're going to calculate all of those intersection points. And there we go. We're almost done at this point. All we did was cast a bunch of rays. Now, you can see here that this does a pretty good job of finding out where light is hitting in the map. And what we have to do here is we then take all those lines and we draw triangles between the lines. And so one extra step here is called a radial sort. And a radial sort is the following. Let me bring up my, my blackboard. So a radial sort, let's say we have a point here. I got to bring up my brush. Okay. So I've got a point in the middle, right? This is my light source. And I've got a bunch of points out here that my rays have intersected with, okay? So here I have all those intersection points. Let me draw all of these because I do want to have a decent example of this. So this is sort of what we have in that the light and sight example. We've calculated the closest intersections from our light source outward in all directions. So this is what we're left with. And now what we want to do is we want to take each of these, let me try and find a good color here. We want to take each of these lines that we have, the intersection lines, or the rays, and we want to draw triangles between them. So we want to do this. We want to go from one point to the next point, and we want to draw these triangles, right? And by drawing the triangles, we get the effect of covering that area with light or covering it with darkness. But the problem is, maybe we calculated this point first and this point second, and this point was third, and this point was fourth, and this point was fifth, right? We don't necessarily calculate those in the correct order to draw the triangles. And so what we have to do is actually do something called a radial sort of these points. And so I'm not going to go over the math for that. I gotta leave something for you guys to do, right? So what we can do here in order to do a radial sort is let's just draw the 0 angle line around the x-axis. So we're going to start here. And then what we can do is we can use another formula, which you have learned in this course, to get the angle between all the rays and this angle, okay, and this line. So we have this angle, we have this angle, we have this angle and this angle, and we're going to sort our rays such that they go in order of that angle. And so what we get once we do that is that this will be the first one, this will be the second one, this will be the third one, fourth one, fifth one, sixth one, seventh, eighth, ninth, and then 10th. And then all we have to do in order to draw the triangles is go from point 1 to point 2. And so the origin 1 and 2, that's one triangle. The origin 2 and 3, that's another triangle. The origin 3 and 4, that's another triangle. The origin 4 and 5. So you go the origin, point N, and point N plus 1. And those are the triangles that we actually want to draw. Okay? So here, and then we go from the last one back to the first one. So that's how we do this radial sort and then drawing of the triangles. Okay. So back to the website, that's how we go from this down to here. Okay. But as you can see, look at what's happening here. We're actually getting some jitteriness around the corners of the map. And that's not good. We don't want jitteriness. Why do we get these jitteriness? Well, there's a couple of reasons. The first reason is the following, right? Look at what we did here. So I actually want to take this example and I'm going to screenshot that and bring it over into, oh no, exposed my Blackboard. Actually, I can just draw this example in the Blackboard. So let's go back to the Blackboard. Okay, we're going to erase this. We're going to do another example. Okay, so let's say I've got one of my obstacles here, and I've got my bounds of the level like this. So I'm drawing rays out from a given point. Okay, so here's my point, for example. Okay, now if I'm drawing rays out like this at a fixed angle, what's going to happen is that one of my rays, might be like this. Okay, so here's one of my rays. It goes, it doesn't hit any objects, but it does hit the end of the level. And then the next ray comes here like this, right? Because this is the delta angle that I've been drawing my rays at. And if we just use the straight up formula that we had last time, then what happens is that we're going to be drawing the triangle, right? The triangle is going to be drawn between this point and this point. And as you can see, that actually clips over the edge of one of the objects. Okay. That sucks. We don't want to actually do that. That's not the correct answer. And not only that, but it does produce jittery effects that we don't want as well. So when you go from here, right, you can see this sort of discrete thing happening at the edge of this triangle that we just showed, or the bottom, the corner right here where I'm circling, that's where this effect is now happening. So if we go down to the triangles, we can see that exact effect clipping over, and that's why we get this sort of jitteriness. But here's the thing. You don't actually have to send rays out like that, because we know from the definition of our problem that light is either going to hit objects or it's not going to hit objects. And the only place where light can transition from hitting an object to not hitting an object is at the vertex of an object. Okay, so what does that mean? It means that instead of sending out rays in all directions, all we have to do now is send out rays toward all the vertices of all the objects. And so that's what this is. Okay? The only other thing we have to do is a very Oh, okay, let me go to the next part. And then when we go from this, now when we draw our triangles, what we get is something much smoother. See? So if we're only casting rays to the edges of the objects, then we're no longer having that case that we talked about over here on the blackboard. Okay? So what we're going to do, instead of sending rays out in all directions, what we do is we send rays out. Oops, that's a bad color. We send these rays out at all the different vertices. So we're going to send rays out like this. Okay? Like that. So we're sending them at the vertices and calculating where they hit. But of course, this one would hit here, this one would hit here, this one would hit here, etc. And so the only other thing that we have to do is we want this ray not really to intersect here because we want to draw the triangle. So for example, if we have this one here, we want to draw this triangle that extends the ray all the way to the edge, but we currently don't have that ray. And so what they do in the tutorial is when they cast rays, they cast one ray directly at the vertex, one ray, so this might be the ray at the vertex, they cast one ray like a fraction of an angle to the left and another ray a fraction of an angle to the right. And what that does is one ray will be a fraction to the right and one ray will be a fraction to the left. The one that's a fraction to the left will not intersect that vertex and we'll have the triangle that we want. Okay? So that's what they're doing here. So if we go back, now we get this really smooth example here. And if we didn't draw these line segments, then you would have essentially the red area just being where there's light. And so now what you can do is maybe if you want to have this like fuzzy shadow, right? So the black area is before we colored the lit area red, but now we're just coloring, we're coloring the whole thing black and we draw white where the red used to be, right? So here we see everything was white and we colored the triangles red, but now we have everything was black and we're coloring the triangles white. And so that's how we get this. And you can create different effects around the edges by just casting multiple rays and maybe scaling those things, okay? So here, what they did is you just have two images and you can blend them together using an alpha mask, okay? So instead of just drawing colors, you have an alpha mask which says, well, if it was under the white thing, then I'm drawing one image, and if it was under the black thing, then I'm drawing another image, okay? And that's it. That's the tutorial. And you're going to have to implement this for the project in some form, where you can have a room that you enter that part of it is dark and part of it is light based on a light source. In assignment 4, what we're going to do, if I can just pull up assignment 4 real quick, is we're not going to be going into the full lighting example, but we are going to be doing the following. No, that's not it. Okay. What's going on with my assignment 4? Okay, this is my assignment 4. I'm going to turn on the desktop audio as well, because I want you guys to hear this. This is the music we're going to have in assignment 4. But in assignment 4, how we're going to use this is we're going to go into a level, and there are different enemies, and some of them have different things based on line of sight calculations. Okay? So let me turn down that music just a little bit. So how's the voice compared to the music? Are the levels okay? I can't hear both at the same time. So here, we have this enemy over here. Oh no, I disabled the... Crap, I disabled the drawing. Essentially what we have, let me, rather than show you the debug drawing in the game, I'll bring this over into the blackboard. Okay, so I'll bring this over into the blackboard. We can bring it over here like this. Okay. Now let's go to the blackboard. So let me stop the music, actually. That might be a bit annoying. So what we have is an enemy over here, and this enemy has a position and it has a bounding box, and my sprite here has a position and a bounding box. And this tree has a bounding box as well. And in assignment 4, we're going to be able to define bounding boxes as being able to block movement or being able to block vision, or both or neither. So here, this one is set up to block vision. And so what happens is that I'm going to draw a line segment between the center of me and the center of the enemy. And if this line segment is uninterrupted, that means the enemy can see me. And so if an enemy that has a certain AI behavior, which we'll get into a bit later, can actually see me, then it will start moving towards me. And if it can't see me, then it will move back to its origin. So if we go back to the game, I don't have the debug drawing on right now, I apologize, but you can see here that the center of the entity, it can't see me. But if I move up a little bit, oh, you can't see this, sorry. So here, this tree is in the way, and so it cannot see me behind the tree. But if I move up enough, now it can see me and it starts to head towards me. But if I go behind these blocks over here, it can't see me anymore and it goes back toward its home. Okay, so that's how we're going to use this for assignment 4. And just one more example over here. These entities have been set up to block vision. And this guy over here comes toward me when vision isn't blocked. And so you get this really cool effect of this entity only being able to come toward me when these guys line up in a certain pattern. Okay, so that's how we're going to be using this for assignment 4. Cool. There's another cool tutorial here on the Red Blob Games article, and you can go, or let's see if I can go there real quick. Okay, so he has Red Blob Games is really cool, has lots of cool things, and you can see here how you can take this exact thing that we just did and make this really cool effect, just like Third Eye Crime. And not only that, but you get these really cool effects like windows, where you have these little slits in the wall and you get these window effects like that. So he goes through the same sort of tutorial, right? Except you can move objects around and stuff inside the game. Right? And so here you can place it, and then you can see how cool this looks just by drawing an image and cutting off the image at the end. Okay, so have a look at those 2 tutorials and create really cool special effects for your project. All right, let's see. We are actually done the lecture. Wow, record time for a 4300 lecture. That's all I had for today. It was only an hour long. And so thanks for tuning in. I'll let you go early today. And I'll see you on Tuesday.